run through probability density functions and some properties there. So PDF in this situation means probability density function. We use that to compute probabilities of continuous variables. So binomial is discrete. This is continuous. This properties, though, have to be the same as before. In other words, the total probability equals 1. Every probability must be greater than or equal to 0. You can't have a negative probability, and they all have to add up to 1. So the first thing I'm going to do is just give you a scenario, a situation where this might be useful. We're going to look at what the density function would look like if we drew a graph of it, and then answer some questions based off that graph. So, suppose that the United Parcel Service is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. So at x equals 0, that's at 10 o'clock. 11 o'clock would be at x equals 60. I'm doing 1-minute intervals in between. And each of those is equally likely. That is to say, your package is just as likely to arrive between 10:15 and 10:16 as it is to arrive between 10:40 and 10:41. The random variable x can be any value in the interval 0 to 60. Okay, this is a situation that's called a uniform probability distribution. It's uniform, everything has the same probability. No matter what interval I pick in there, every minute it is equally likely that your package will arrive at that minute. So if I have 60 total minutes, and the probability is, total probability has to be 1, what would be the probability that my package would arrive at 10:01?
1/60th.
1/60th. 10:02 is also 1/60th. 10:03 is 1/60th. So each of these has probability of 1/60th. That's what's shown in this graph. We graphed binomial distributions, and we just listed each x value and drew a line going up to it. Because now we're talking about continuous. Our graph is not just a series of lines. It's a shape with shading underneath. Since this is uniform, everything has the same probability. 1/60th is the height. Each minute had a probability of 1/60th. My x values went from 0 to 60. So this gives me my graph. The shading, that area under that curve, represents the probability. So if I said the probability that it arrives between 10 and 10:30, okay, so if I'm saying this is x equals 30, then that probability would just be what's the area of this half of the rectangle. And we could calculate that. Area is length times width for a rectangle, right? What's the length of this rectangle? But if I only did, let's say, 30, my length would be 30. My height is 1/60, so probability is 1/2 or 0.5. There's 0.5% chance it arrives between 10 and 10:30. And we could calculate any probability that we wanted there by finding that area. You guys okay with this part? Okay, so let's answer some questions. So my slides are frozen. Oh no, this is useful. Okay, find the probability of choosing a time between 15 and 30 minutes. So we really just have to do length times width. How far is it from 15 to 30? Right. You find your x is just 30 minus 15, which is 15. So the probability is just the area of that rectangle in that situation, which my length would be 15. The height of that rectangle is
1/60.
And you get 1/4 or 0.25. So there is a 25% chance that you will get your package between 10:15 and 10:30. All right, I'm going to flip this around. There is a 30% chance your package will arrive within the next blank minutes.
So you have to go backwards.
So I don't know my number of minutes, but I know my probability is 1/60th.
So it's 60 equals 1.3.
Oh. Sorry. So you got the 1/60th as the probability. You said it equals point. Okay.
So you divide it by
Are we with that? Okay. So divide by 1/60th or multiply by 60.
equals 18.
So there is a 30% chance that you will get your package in the next 18 minutes.
Are we gonna have to write these as sentences or?
Okay. Questions there? So if I were to look at a histogram of my relative frequencies, we know that anything that is symmetric and nice and symmetric, we've called those bell-shaped in the past. Those represent what we call the normal curve. So we've looked at frequency, or we've looked at histograms before, and we've said skewed left, skewed right, bell-shaped. Now we're learning bell-shaped is normal. That's what our normal curve looks like. Because the normal curve is continuous, we won't see it as rectangles. We will see just a nice smooth curve with shading underneath. In this, that peak of your normal curve represents your mean. And the second important thing, these are called inflection points right here. That's when the curve of my graph changes. You know, so this is kind of like curving downward and then it changes direction. That always happens within one standard deviation. So like the mean plus one standard deviation and the mean minus one standard deviation. We will be using this more as time goes on, but I really printed these notes for you so you would have this diagram as we went through. So I could give you a picture of a normal curve and ask you questions like what is the mean and standard deviation. Let's say I gave you this picture. Let's say this is 6 and 9. So a few of your homework problems are just going to give you a diagram like this and say what is the mean, what is your standard deviation, just from looking at this curve. And we know the mean is where we have the peak of our graph, so the mean is
10%.
okay. To get your standard deviation, you have to look at these inflection points, so where my graph kind of curves the other direction. Those happen at 6 and 9. The standard deviation is how far those are from the mean. So 7.5 minus 6 is 1.5. 9 minus 7.5 is 1.5. So my standard deviation is 1.5 here. Is that okay? So some properties of the normal curve that we will look at. It's always symmetric about the mean. So that means the probability of being above the mean is 50%, probability of being below the mean is 50%. It is the center. The mean, median, and mode are all equal in this graph, so you will have a single peak. That mean is the same as your median and mode. We talked about the inflection points. Total area is 1 because it's a probability. I already mentioned that. And the last thing, we haven't seen the empirical rule in a bit, but it comes back into play here. So the empirical rule, remember we did that at the beginning, and it told you a certain percent of your data had to fall within a certain distance of your mean. So I put this next slide up here to remind you. Remember, you still have your formula sheet which has that. But the empirical rule says 68% of the data has to fall within one standard deviation of the mean. Okay, so if there's my mean, that means half would be below and half would be above. So 34 below and 34 above. Within 2 standard deviations, you have 95%. So these little rectangles would have to be 13.5. And then within 3 standard deviations is 99.7%. So this just kind of gives you the breakdown in the diagram. We did those questions back when we talked about the empirical rule. I would say, you know, what percent of your data falls within 1 standard deviation below and 3 standard deviations above the mean. And we had to try to figure that out. This diagram just kind of gives you a breakdown of that rule that we've seen before. Do you guys remember talking about that one? Are there any questions? So now I just want to do a few examples. This one. So this data represents the heights in inches of a random sample of 52-year-old males. Draw a histogram of the data using a lower class limit of the first class equal to 31.5 and a class width of 1. So we can do histograms by hand or on our calculator. I've given you all this data, and I think I was even nice and put it in increasing order, so it shouldn't be that hard to do it by hand. So let's draw this out. So my x-axis, I told you we are going to do a lower class limit. So our first one is going to start at 31.5. We're going to go up by 1 each time. So this would be like 32.5, 33.5. I'm just labeling every other one. Try to space this out evenly. We could graph frequencies, or let's do relative frequencies. And this is our height. Okay, so I told you there were 50 points here. So this first rectangle that I would draw would be all the data that's between 31.5 and 32.5. So that would just be 1. Okay, let's divide that. Out of how many total points do we have?
50.
Okay. So to find your probability, you'd have to do 1 out of 50, so that's 0.02. So I'm just going to count by 0.02s here. So the probability of being between 31.5 and 32.5 is just 0.02. Okay, being between 32.5 and 33.5. 4, so 4 out of 50, if I want the relative frequencies, will be 0.08. 33.5 and 34.5. We get 5. Do you guys all know how I'm getting my relative frequency? The number divided by 50, so that's just like your probability. So there is a 0.1, so 10% chance you fall in that group.
Okay, so you're taking like however many there are.
I'm essentially graphing the probability here.
So you take like on that one, you take the 4 divided by 50 to find out where it falls next one.
Okay, now I'm at 34.5 and 35.5. How many do we have there? 10. So 10 out of 50. That one's going all the way up to 0.2, so a big jump there. 35.5 and 36.5. We get 11 that time. So 11 out of 50 gives me 0.22. $36.5 and 37.5. 10 again. 10 out of 50. Give me the 0.2. Okay. 36 or 37.5 and 38.5. Okay, 5. So 5 out of 50 was 0.1. .5 and 39.5, we get 3 out of 50. 0.06. And the last one, 1 out of 50, so 0.02. Okay, so we made our histogram. Now we could have done this on our calculator. We've talked about making them before, but I think we agreed then, as long as we didn't have to like spend a lot of time putting the data in order, it was a little easier just to make them by hand, rather than trying to change all the settings on the calculator to start and stop where we wanted. So the question, part B, do you think that the variable height of 2-year-old males is normally distributed? Does this appear to be normally distributed? Yeah, it looks like we have one peak. It's pretty symmetrical on both sides, so that does appear to follow a normal distribution. So yes, we could look at a histogram to decide that. All right. Any questions there? I might ask you questions about what the probabilities represent, and there's really 2 interpretations that we could use. Area under a normal curve can either represent the proportion of the population with the characteristic, so it could be like saying 10% of the population is in this height range, or it could be the probability that an individual will have that characteristic. So it could be for a random, if I just pick a 2-year-old male, there is a 10% chance they will have that height. So on some of these questions on your homework, it will ask for the 2 interpretations. One is thinking it as a probability. If I select a random person, the probability is this. The other is thinking of it as it represents this proportion of our population. Okay? So we've got a couple examples to finish off. The weight of giraffes are approximately normally distributed with a mean equal to 2,200 pounds and a standard deviation of 200 pounds. Draw a normal curve with the parameters labeled. So part A, you are drawing this nice symmetric curve, single peak about the same distance on both sides. Where does this peak occur? And that is what? Which is what in this problem? Okay, and then these inflection points on each side. That's where the graph kind of changes shape. That's 1 standard deviation away. So you have to do the mean minus and the mean plus. So the mean minus 1 standard deviation would be, and the mean plus 1 standard deviation.
2,400. Not 68 or something.
Yep, 68. It didn't ask us to say that, but if I did, yes. Okay, part B. Shade the area under the normal curve to the left of 2,100 pounds. So 2,100 would fall right in here, halfway between, and we are shading the area to the left of that. Now in the next section we'll talk more about how to find those probabilities. We could use the empirical rule to find it. but we're not going to right now. We're going to save that for tomorrow. Part C just says, suppose that the area under the normal curve to the left of my 2100 is 0.0385. Provide two interpretations of this result. So the first is the proportion of giraffes who weigh, this would be less than 2,100 pounds, is, and then our probability, 0.3085. So it could be saying in our actual population, 30.85% of the giraffes weigh less than 2,100 pounds. The second interpretation is to think of it as a probability. So the probability a giraffe weighs less than 2,100 pounds is 0.3085. So on your homework, some of those questions, you are going to have to be able to write both of those sentences, making sure.
Just the proportion.
Yeah, one's the proportion of the total population, the other is for a random giraffe, what's the probability it'll have this weight.
Like, doesn't like half the probability, like, you can't round up like every giraffe.
Say that again?
Like, this like half the probability, like, 'cause you
Yeah.
can't like round up every single giraffe alive.
Right, it's based off a sample, so not the entire giraffe population. Okay, other questions there? For the last example, I do want to look in your books. So please open up your books, page 363. We're going to look at a couple problems here. If you don't have your books, sit next to somebody that does. Okay, so problem 23. Is everybody looking at that? It's at the very bottom of the page. One graph in the figure on the following page represents a normal distribution with a mean of 10 and standard deviation of 3. The other represents a mean of 10 and a standard deviation of 2. Okay, so if they have the same mean, that tells me my graph should have the same peak. What's that difference in the standard deviation telling me?
Where the data is more spread.
Right. One of them, the bigger the standard deviation, the more spread out the curve is, right? Smaller standard deviation means a skinnier curve. So if you flip to the next page, which one has a standard deviation of 3? So the data is more spread out. Good. So that means A has a standard deviation of 2. It is less spread out, so it's a skinnier looking curve. Does that make sense to everybody? And then problem number 25. So I want you guys to try this one on your own, please. I sketched one example for you. You just need to look at this graph and find the mean and standard deviation of it. I want to make sure you can. And your standard deviation would be? Does everybody get that? Do we need to talk about it at all? I'm done. This is a very short section, so you've got time to work on your homework now. We are going to do you guys have a lot of time